Welcome to this video on Chapter 14. Chapter 14 deals with the kinetics of a particle and in particular how the principle of work and energy can be applied to the kinetics of a particle. The principle of work and energy can be characterized by three attributes, namely forces, velocities, and last but not least, distances. Problems that require you to use the principle of work and energy can be recognized by these three attributes. To illustrate the principle of work and energy in this video, I will be using the example of a climbing aircraft. The aircraft is considered to be a particle subjected to forces W, weight, L, lift, D, drag, and T, thrust. The forces are given to be constant. Furthermore, the aircraft is given to be moving with a constant velocity v. After moving a horizontal distance d and a vertical distance h, the aircraft arrives in a second location. The question is to solve for the velocity of the aircraft in this location. So, what is v2? This question can be answered using the principle of work and energy. The principle of work and energy can be derived starting from the equation of motion of a particle, which we have seen in Chapter 13. The equation of motion states that the sum of forces acting on a particle equals the mass of the particle times the acceleration of the particle. It is possible to integrate the equation of motion over distance. Here we integrate both sides of the equation from distance s1 to distance s2. Let's focus first on the left-hand side of the equation. The left-hand side of this equation is known as the work of a force, denoted by the letter U. Here I've drawn the most general case, where force F is being moved over the dotted line from point 1 to point 2. Let's write down the left-hand side of the equation once again. Now the equation reads, the work done going from point 1 to point 2 equals force F dot product ds. Notice the dot product. This is used because only the component of the force that is tangent to the path contributes to the work done by the force. Theta is the angle between the force and the path. The component of the force tangent to the path therefore equals F cosine theta. Things can be simplified if we have a constant force traveling over a straight line, as drawn here. The component of the force that is tangent to the path equals F cosine theta, where theta is the angle between the force and the path. Because the force is constant, it comes outside of the integral sign, and the work done by the force going from point 1 to point 2 can be written as U12 equals F cosine theta times S2 minus S1. Notice that the work done by this force in this example is positive because the component of the force tangent to the path and the direction of the displacement are in the same direction. In the event the component of the force tangent to the path and the displacement are in opposite direction to each other, the work done becomes negative. This can easily be seen when I would move the force from point 2 to point 1. The work done going from point 2 to point 1 equals F cosine theta S1 minus S2, which equals minus the work done going from point 1 to point 2. Going back to the example of the aircraft, we can now calculate the work done by the aircraft moving over horizontal distance d and vertical distance h. This can be written as the following equation: T minus d times distance d, because both forces are working in the horizontal direction, plus L minus w times h, because both forces are working in the vertical direction. Let's look at another example. Let's consider a particle of mass m. We know that the weight w of the particle can be expressed as m times gravitational acceleration g. Weight is a force, and hence also can do work. For example, if I lift up the particle by a height of delta y, the work done by the weight of the particle becomes U12 equals minus mg delta y. Notice that the work done by moving the particle up is negative because the displacement is in opposite direction of the direction of the force. It does not matter via which path the force travels. The work done by its weight remains the same as long as the difference in height remains the same. Here I've drawn three paths, A, B and C. Because the work or the height difference between the endpoints is the same for all the three paths, the work done by the weight of the particle is the same for all three cases. This is what makes the weight of a force a conservative force. Another example of a conservative force is the force of a spring. Here I consider a linear spring. This means that the spring force is a linear function of the displacement of the spring from unstretched condition S0. The spring force becomes Fs equals K times S. K is a so-called spring stiffness. By stretching the spring over a distance S, the force used to stretch the spring performs work. So if I stretch a spring from unstretched condition to distance S as shown, I can perform the following integration. U12 equals the integral of F ds, which in turn equals the integral of Ks ds. Solving this integral, you get the following equation for work. U12 equals half K times in between brackets S2 squared minus S1 squared. In determining the work done by a spring, it is important to notice the direction of the force. Here I've drawn a particle connected to a spring. Because of the third law of Newton, the force on the particle connected to the spring is equal in magnitude but opposite in direction. Hence, the work experienced by the particle is negative the work experienced by the spring. This is important to remember. Another important thing to note is that springs have an unstretched distance. In computing the work done by a spring, the unstretched distance always needs to be taken into consideration performing the integration. Otherwise, you will get wrong values for the work done by a spring. The work done by a spring, as mentioned before, also is a conservative force. It does not matter which path the force of the spring follows, as long as the locations of the endpoints of the path are known, the work done by the spring for that path is known. Friction is an example of a non-conservative force. Here I consider a block sliding over a rough surface. Before I can calculate the work required to slide the block over a distance d, I need to complete the free body diagram for the block. Apart from force P, the block experiences a force due to its weight W, normal force N, and friction force F, which equals mu K, the dynamic friction coefficient, times normal force N. The work done by force P is straightforward to calculate. It equals P times D. The work done by the friction force equals minus mu K times N times D. Notice that the work done by the friction force is negative because its direction is opposite to the direction of the displacement. However, if I reverse the direction of the displacement, the friction force will switch direction as well and will remain opposite to the direction of displacement. This means that the work done by the friction will be different if I displace the block 1 meter from point 1 to point 2 in a continuous fashion than if I would move the block first 10 centimeters to the right, then 5 centimeters to the left in a repetitive fashion until I reach point 2. The work done by the friction force is dependent on the path, and therefore it is a non-conservative force. Now let's go back to the equation of motion. So far we have focused on what happens to the left-hand side after integration. Now I would like to focus on the right-hand side. From chapter 12 we know that ADS equals V dV. By substituting this in the right-hand side of the equation, we can rewrite the integral in the following form. the integration from V1 to V2 for mv dv. Notice the dot product on both sides of the equal sign. If we assume the mass to be constant, this equation can be solved in the following way, namely a half m times v2 squared minus v1 squared. You probably recognize this equation as the kinetic energy of a particle, which in full we can write as T equals a half mv squared. Notice that the kinetic energy of a particle is always positive. Now we have integrated both sides of the equation of motion over distance, we can formulate the principle of work and energy, which states that the kinetic energy in point 1 plus the work done on the particle equals the kinetic energy in point 2. Or, in a formula, T1 plus U12 equals T2. Going back to the example of our climbing aircraft, we now have all the elements we need to solve for the velocity in location 2. The kinetic energy of the aircraft in location 1 equals a half mv v1 squared, and the kinetic energy of the aircraft in location 2 equals a half mv v2 squared. The principle of work and energy states that the kinetic energy in location 1 plus the work done going from location 1 to location 2 equals the kinetic energy in location 2. Now it's only a matter of rearranging terms. This results in the equation that v2 equals the square root of v1 squared plus 2 times the work done going from location 1 to 2 divided by m. Here we can still substitute the work done going from point 1 to point 2 as we have determined earlier. However, I will leave this to the lecture to explain in more detail. Before, I made a distinction between conservative forces and non-conservative forces, where I stated that the force is conservative if the work done is independent on the path. A force is non-conservative when the work done is dependent on the path. This distinction is important to make for a special group of problems, namely problems where a particle is only subjected to conservative forces. In this case, the particle of the energy will be conserved. This means that the work done by the conservative forces can be considered as a form of energy, namely potential energy. For the weight of a particle, the potential energy can be written as Vy equals plus minus W times Y. Whether the energy is positive or negative depends on the context of the problem. For a spring, the potential energy can be written as Ve equals plus minus a half Ks squared. Also here, the plus or minus sign needs to be determined from the context of the problem. Conservation of energy states that the kinetic energy plus the potential energy of a particle in location 1 equals the potential energy plus the kinetic energy of a particle in point 2. Or in an equation, T1 plus V1 equals T2 plus V2. There are many examples where a particle exchanges potential energy for kinetic energy, or vice versa. This can all be considered using the conservation of energy. Note that it's only valid to use conservation of energy if there are no non-conservative forces acting on the particle. Now that we have established the principle of work and energy and the conservation of energy, there is one other concept that I would like to introduce briefly, namely power. Power is the time rate of doing work. Its unit is joule per second, which is also known as watt. Power can be used to express efficiency of a mechanical system. With that I mean the ratio between the power put into the system and the power that comes out of the system. In an equation we can write epsilon equals power out divided by power in. Because in real life systems we always have power losses, the efficiency always is smaller than 1. To conclude, in this video I've shown how the principle of work and energy can be derived by integrating the equation of motion of a particle over distance. This results in the equation as shown, where the kinetic energy of the particle in point 1 plus the work done by moving the particle from point 1 to point 2 equals the kinetic energy of the particle in point 2. For particles only subjected to conservative forces, the conservation of energy applies. This states that the kinetic energy plus the potential energy in point 1 equals the kinetic energy and the potential energy of the particle in point 2. Apart from that, I have discussed the concepts of power and efficiency. During the lecture, the content of this video will be demonstrated using several examples. I hope to see you there.